Okay, time to start. Welcome to the secret seminar. Today's speaker here, Dr. Chan Park from IBS. He will today talk about gravitational wave background and pulsar timing array. Please start.
Yeah, thank you for introducing. Firstly, I am sorry about I cannot go showcase today due to the financial problem of my research group. And I appreciate Dr. Won Lee for inviting me and giving opportunity to present my work and this topic. Okay, today I will talk about the gravitational wave background and pulsar timing array. And recently, pulsar timing arrays over the world report the strong evidence about gravitational wave background. So I will talk about the nature of gravitational wave background and the working principle of pulsar timing array. These are my motivation of talks, and I think that the second wave of gravitational wave astronomy is coming. So I think it is a big event. But we have having the strong evidence for gravitational wave background is a very big event for gravitational wave astronomy, and actually its main target for pulsar timing array is the gravitational wave background from supermassive black holes binary. But there are possible scenarios for frequency band and the sensitivity level of pulsar timing array. So the supermassive black hole is not conclusive. So we have much space to propose a new scenario for the gravitational wave background, and I will show you about this space. And I'll give an intensive Beijing lecture for gravitational wave background for astrophysicists, and I will talk about I will show the working principle of each detectors. Okay, let me start. For your reference, I summarized the PTAB publications in June 29. It is the number of papers about 20. And there are many. These papers are written by 5 collaboration, and EPTA is a European PTA, and MPTA is the Indian PTA. They collaborate to write this paper. And PPTA is the Parkes pulsar timing array. Actually, Parkes telescope is located at Australia, and so this collaboration is Australian collaboration. And Nanograv is the collaboration of North America group, North America researchers, and Nanograv utilized the Greenbanks telescope and Arecibo telescope, but the Arecibo telescope passed away quite recently, and there are papers from China pulsar timing array also. Okay, this overview of my talk. Firstly, I introduce gravitational background. And secondly, I use noise reduction by correlation method. Oh, yeah, there is there any on mic? Yeah, okay. And I introduce pulsar timing array, and as a source for gravitational wave background, I consider supermassive black hole binary, and I I will show the another possibility, and I will, if I have a time, then I will propose a new detection method utilizing SKA. SK. And this picture is the for the UGMRT. UGMRT is abbreviation for upgraded giant meter radio telescope, and it is located at Pune, India. And I'm also member of India Pulsar Timing Array collaboration. Okay, let me start. I will introduce gravitational waves. I summarize the properties of a gravitational wave in this slide, and actually the propagation speed of a gravitational wave is identical to the speed of light. And if we introduce transverse traceless gauge, then each propagation direction is orthogonal to the tidal direction. It means that, for example, the XY plane is the tidal plane. So the tidal pulses are exerted on XY plane, and gravitational waves are propagating to Z. So their propagation directions and tidal directions are orthogonal to each other. And second property is the no expansion of tidal plane. It means that the gravitational wave can change the area, can change the shape, but the gravitational wave cannot change the area. So this animation shows the motion of test masses when gravitational wave is passed through the Z directions. Then it's gravitational wave can change its shape, but the area is preserved even gravitational wave passes. And the gravitational wave has two polarization modes. The most popular basis to present polarization mode is plus polarization and cross polarization. So, and I will let me discuss the detail of a gravitational wave. Let's consider the metric perturbation h mu nu, and in Cartesian coordinate, the component of this metric perturbation is much smaller than 1, and metric component has a background part, eta mu nu, and metric perturbation part, and the effect of gravitational wave is are constrained on the XY plane, so it has only XY component like that. And H mu nu have a property of has a traceless condition, so this component has an opposite side, and H mu nu is a symmetric tensor, so this off diagonal components are identical to each other. And let me consider the infinitesimal displacement dl, and dl is the displacement on the xy plane, and it has an angle alpha with respect to x-axis. Then the component of this vector is given by this four number: 0, dl cosine alpha, dl sine alpha, and 0. Then the physical length of dl is given by this formula, and actually it is in a product is given by metric. Metric is given by eta plus h mu nu. Then the up to first order, the root of dl square is given by this formula, and it is proportional to dr, and there are background term, and there are first order terms. And let's consider first h plus part, first term. Then if we put the alpha as 0, then it gives a plus contribution, this represented by yellow arrow. then if we put the alpha into the pi over 2, then it contribute to minus. So this yellow arrow shows the minus contribution for the angle of this direction. So the total physical length is flattened by have this shape. And if we consider the next term, h cross term, and if we put the alpha into as a pi over 4, then it contributes to it has a plus contribution as a like yellow arrow in this figure. And if we put alpha as a minus pi over 4, then it contributes to minus contribution like that. So its total shape is tilted to this shape by 45 degree. And if we give the oscillation factor for this metric perturbation, then the shape will be changed like this animations. So this oscillation factor is the wave to the z directions. So it represented the gravitational wave propagated to z direction, and the tidal force will be exerted to the xy plane, and it has a two polarization model like these animations. Okay, let's move to stochastic gravitational wave part. Is there any question up to now? Okay, let's go further. Okay, I want to generalize gravitational wave. So firstly, I consider monochromatic plane gravitational waves, and it has a complex amplitude h tilde, and it has a phase I omega minus t plus kappa dot x, and kappa is the unit vector for propagation of a gravitational wave. Then omega is the angular frequency, and the metric perturbation is given by a real part of this complex tensor. And by the gauge condition, the complex amplitude have to be satisfied these three conditions, and n is the time like normal vector. Okay, and the complex amplitude can have two bases. First one is plus polarization, and second one is cross polarization. And I used this 1/2 factor because this factor gives the orthonormal condition like that. So I prefer put this factor in the polarization basis. Then if we introduce this basis, then amplitude of gravitational wave can be decomposed into two polarization part, and each amplitude is called by h plus tilde and h cross tilde. And this is the simplifying notation using summation notation. And even if introducing Einstein summation convention, then we can omit this summation notation. And I'll extend to the plane gravitational wave. The plane gravitational wave is given by the integration over all frequency of monochromatic plane waves. So the amplitude is becomes the function of frequency. And because I give the because h should be real tensor, so the complex amplitude have to be satisfied this condition. And complex amplitude can be decomposed into the using this polarization basis like that. And this slide shows the full generalization propagation of gravitational wave, we consider the all frequency and all direction of gravitational waves, then the amplitude of gravitational wave is can become function of omega and kappa. Kappa is the direction of gravitational wave. And integration d scale kappa means that the integration of all direction. And if we introduce polar and azimuthal angle for kappa, then the integration becomes like that. Then the complex amplitude can be decomposed using this basis tensor, but this basis is function of kappa. Actually, this tensor lives in the orthogonal plane to kappa. So for the different kappas, the basis should be changed. From the real condition for HAB, so H tilde have to be satisfied these conditions. Then if we introduce this complex amplitude, then all information of gravitational wave can be encoded in this complex amplitude. Okay, let's consider stochastic gravitational waves. For example, the stock is the is an example of a stochastic process. So so gravitational wave can be random. So then if we consider this kind of stochastic gravitational wave, then H tilde amplitude will be a statistical random variable. So we have to be consider each first moment or second moment like that. Then if we give information for the first moment or second moment or for gravitational wave amplitude, then its statistical behavior is determined from these conditions. Okay,
so question about the bracket.
Okay,
is it average over the time or space, or what is that bracket means?
Bracket means the ensemble average.
Ensemble average. How do you form the ensemble?
Infinitely many ensemble of our universe. Yes.
Oh, I see. So you are talking about, I see, stochastic gravity. But in practice, it may be essentially the time average or space average.
Yeah, by ergodic hypothesis, it can be replaced by time average.
Okay, it can be replaced. Yes. Okay.
Okay, let's move to next section. In this section, I introduce gravitational wave background. Actually, gravitational wave background has a random property, so we have to consider a gravitational wave is a kind of stochastic gravitational waves. There are two origins for gravitational wave background. First one is cosmological origin, and second one is astrophysical origin. In early universe, the hot state of matter is essentially quantum state. So its coupled gravitational wave have to be statistically random. So gravitational wave from generated by early universe is a stochastic gravitational wave. So it forms gravitational wave background in our universe. And second origin is astrophysical origin. Actually, in our current universe, there are many binaries of compact stars. So each event we cannot resolve each event, but this distribution can form a background of gravitational waves. So this kind of gravitational wave background has a origin is a astrophysical origin gravitational wave background. And I will introduce statistical assumptions on gravitational wave background. And actually, our case is similar to the water wave generated by raindrops, and if we put the lip on the water, then the motion of lip has a each motion will be a random because the distribution of raindrops are random. So each generates water waves, and the superposition of it all of each individual random wave will generate random stochastic motion. So first assumption is Gaussian assumption. It means that the first and second moment fully determine statistics. So actually, if the sources are infinitely many, then we can introduce this Gaussian assumption. So introducing this assumption is very reasonable. And second assumption is the stationary assumption. If actually our cosmological time scale is 13 billion years, but our observational time is much smaller than the cosmological scale. So for our observation time, we can assume the statistical property is not changed over time. So this stationary assumption is also reasonable. And third assumption is isotropic assumption. It means at a point of space-time, the statistical effect from random wave from all directions are identical. Because our universe is homogeneous, so each random distribution make random waves, and each superposition will have a isotropic property. And fourth assumption is no prefer polarization assumption. Actually, there is no reason to prefer one of a polarization of gravitational wave. So this assumption is also reasonable for gravitational wave background.
So can I have a question? So
yes, you can.
Can you explain more about the Gaussian assumptions more intuitively?
Actually, the infinitely many events of the actual how can I say the it actually first and second moment. First moment means the average, and second moment means the variance or standard deviation. And Gaussian distribution is perfectly described by mean and standard deviation. And for in general sense, Gaussian assumption means that first and second moment fully determine statistics. And if we put the lip on this water wave, and let us consider each motion and its probability for the position to the equilibrium point, then each position, average of each position will be equilibrium point. But each variance, it will have a variance, and the statistical distribution of a position will have a Gaussian shape if the number of events or number of raindrops are infinitely many. So, and for gravitational wave, it exerts the tidal force, and the test mass will oscillate by a stochastic gravitational wave. Then its motion, average of each motion will be equilibrium point, and its statistical distribution or position will be Gaussian. Can you?
Thank you.
Okay, thank you.
Hello, I have one question about
the
stationary assumption. Is this assumption also right for the early universe?
What assumption? I can.
A stationary assumption is still
Stationary
right
assumption.
for the Earth universe or just for lifetime universe?
Okay. In our current universe, the cosmological evolution timescale is 13 billion years, as you know.
Yeah.
Our observation time is just only 10 year or 15 year, for example, pulse timing array. So our observation time scale is much smaller than the cosmological evolution time scale. So
Yes.
we only consider the this property. But if the source is not enough, so the number of sources is not enough, then we cannot assume this stationary assumption, because for astrophysical origin, if source is sparse, but then the signal will be the event of signal is discontinuous. Then in this case, we cannot assume the stationarity. So for this case, we have to introduce another special treatment for the data analysis for gravitational background.
Okay, yeah.
Yes.
Thank you.
But in this talk, I will just only consider stationary gravitational background for simple.
Okay.
Okay.
Yeah, thanks.
These are mathematical representation of four assumptions. First, Gaussian and stationary assumption is given by these two formula. First one is the ensemble average of gravitational wave amplitude, and we can consider it is equal to 0. And second formula shows the second moment of gravitational wave amplitude, and each amplitude has different frequency and different directions. Then stationary assumption is represented by this second moment is proportional to delta function. Delta inside delta function delta omega minus omega prime, and actually it is stationary, but it has a spectral property. So it can have a proportional function as a function of omega. Then it is called power spectral density. And by definition, this is the real and even function. And for isotropic assumption, then the second moment of gravitational wave amplitude is proportional to delta scale chi minus chi prime. It is defined by these two one-dimensional delta function using theta and pi. And fourth assumption is no prepopularization assumption. Then the second moment of gravitational wave amplitude is proportional to lambda tensor. Actually, lambda tensor is can be generated by each basis using basis of gravitational wave. And if we using the projection operator for UV plane, then it can be also generated by this formula. Actually, this operation is actually the all length tensor using this operation then will be projected to UV plane, and using this symmetrization. So using after with this operation, all length tensor will be tangent to UV plane, and it has to be symmetric. And this operation remove the traceless part. So after operating these two operations, we only have a traceless symmetry length to tensor. Actually, lambda, the role of lambda tensor is the projection operator for symmetric traceless length tensor in UV plane. It means that we have no prepopularization. Okay, it's a final result for second method of gravitational wave background. So if we put all these things, then we can get this formula, and 2 pi or 4 pi 1/2 is the normalization some factor. And our in this statistical assumption, the all information of gravitational wave can be encoded in power spectral density function SH omega. So SH omega is a central quantity for in the gravitational wave background. And this is the amplitude scale of gravitational wave. And after some calculation, it is the frequency integration of power spectral density over all frequency. So this formula justified the name of SH. That is the power spectral density. And usual text in this formula, there are exotic factor 4 in this in right hand side, but it comes from the careless normalization of basis. So I prefer the normalized basis. So if we use the normalized basis, then there is no there is no exotic factor 4. And I introduced another quantity for gravitational wave background. Actually, gravitational wave has an energy density. So in cosmological situation, it is easier. It is a more easier for physicists to convert conversion having conversion to energy unit. Then the rho GW is the energy density for gravitational wave background, and it is given by this formula. Then there is a time derivative for gravitational wave amplitude. So we have a omega scale factor, and so rho omega CW is a integration of omega scale SH over all frequency. Then actually omega can have a negative value, but in physical frequency, frequency is a positive value. So this is another convention to writing integration. And if we introduce frequency, then the domain is restricted from 0 to infinity. Then the power spectral density function is changed by one-sided power spectral density like that. And omega GW quantity is defined by this formula. Actually, in this omega, this is the cosmological parameter. Omega rho GW over rho C is the critical density for current universe. So this quantity is identical to omega GW, but in the gravitational wave committee, omega GW means the density over log frequency of cosmological parameter. So this quantity has some advantage because in the actually x-axis is log f and y-axis is omega GW. Then by integration by, you can integrate the curve by I, then you can get cosmological parameter value from just integrating by your I. So omega GW is a very convenient quantity in this figure. Then omega GW is related to the one-sided power spectral density like that, and it is proportional. Omega GW and SH is proportional to each other, and it has a f cubic factor. And this figure shows the spectrum of stochastic gravitational wave background, and the frequency from 10 to the minus 18 to 10 to the 4, and y-axis shows the omega GW value. So and gray line shows the inflation model, gravitational wave background from inflation model, and in a very low frequency, you can observe gravitational wave by the polarization mode of CMB. Actually, the B mode of CMB is coupled to stochastic gravitational wave background. So by measuring B mode of CMB, then you can extract information about the gravitational wave background in this frequency band. And on the nano-LH gravitational band, nano-LH frequency band, then pulsar timing array can observe the gravitational wave background in the nano-LH band. And in this band, supermassive binary black hole inside the core of each galaxy can form this background, this gravitational wave background. And for the higher frequency, Lisa and LIGO can observe the gravitational wave background like that. And green line shows the gravitational wave background from binary black hole model, and blue line shows the neutron star model. Okay, up to now, is there any question? Okay, let's move to
Okay, I have some question.
Yes.
So why, as for the CMB, the frequency range of CMB,
Yes.
essentially it's due to the, I guess, redshift, right?
Yes, right, yes.
So
it's
that this corresponds to roughly, I mean, the what time? So so in terms of energy or something, so what energy scale that they were produced to be observed through the CMB?
As I know, the CMB is generated at 3000 Kelvin. Actually, I'm not an expert on cosmology, but so the CMB is the print of the early universe when our universe has 3000 Kelvin. Then this is the this is determined by the B mode is determined by gravitational wave background at our universe was 3000 Kelvin. It's the only.
No, I mean, then I'm very much confused because that is roughly the redshift factor 1100 or something, right?
Yes, 11.
And considering the then so what you are saying is that we cannot see any information about the gravitational wave that were produced before the recombination time through CMB. That's somehow confusing. I mean, the main thing is that we'd like to understand for the earlier universe, even way before decoupling time, right?
Yes. But I'm sorry, I don't know very much the cosmological scenario before the CMB.
Okay.
Answer. I'm sorry.
Okay. Okay. Thank you.
Okay. Let's move to the next part. This is the noise reduction. I will introduce the noise reduction method because it is the very important principle, working principle for pulsar timing array. So I will intensively introduce this topic. Actually, there are terms in gravitational wave physics: output, signal, and noise. Output means the proportion of signal and noise, and H is the signal and N is the noise. S is not signal, S is the output, and H is the signal. Don't be confused about that. And the gravitational wave signal actually comes from some projection of gravitational wave amplitude. So in this formula, we use the detector tensor dθ. So it gives the projection of some projection of gravitational wave amplitude. So this is the scalar quantity we can get from the detector. X0 is the location of the detector. So it is a function of time, only time. Then noise has this spectral N tilde is the Fourier transform of noise, and noise is a function of time. And it noise if noise is random, then it has we assume that the statistics of noise as and we introduce two assumptions for noise, and first one is Gaussian and second one is stationary noise. So its average is equal to 0, and its second moment is proportional to delta function because it is stationary, and it has a spectral property, and this spectral property is encoded in the noise spectral density function S and omega, and by definition it's real and even function. And but as I mentioned earlier, gravitational wave background and noise has identical statistical behavior. So how to distinguish gravitational wave from noise? It is a very difficult problem. But to distinguish gravitational wave from noise, I will introduce correlation method. For example, we have two detectors, but the gravitational waves are identical for two detectors, and each detector has a different noise. But each output will be a summation of gravitational wave signal and noise. So if we correlate output from two detectors, we have four terms, but each this cross terms will be uncorrelated because there is no correlation between this pair. But this correlation will be amplified by correlation. So if we increasing observation time, the correlation of a gravitational wave signal is proportional to t, but other terms is proportional to square of t. So if we measure enough, if we have enough measurement time, then we can amplify signal relative to other terms, other uncorrelated terms. So it's exact form for correlation measure Y, and S1 is the output from one detector, and S2 is output from second detector, and Q is some filter function. Then if we define correlation like that, it is identical to frequency integration of this factor over frequency. And I define the signal as the expectation of Y. Then by the expectation, by the averaging, we only have two terms from gravitational wave. So actually, by some calculation, this correlation is proportional to observational time and pulse spectral density for gravitational wave background, and some factor gamma tilde. Gamma tilde is we call it as overlap reduction function, and it depends on the location of deployment of detectors, two detectors. And actually, final result signal is proportional to time, observation time, and it is integration of these three factors. And first one is power spectral density of gravitational background. It is overlap reduction function. It is filter function. And noise is defined by standard deviation of y when there is no gravitational waves. Then final result is noise scale is proportional to t. So noise is proportional to square root to t. Then by using our definition of signal and noise, so each signal to noise ratio is proportional to square root to t and with some factors. And if we choose carefully filter function to maximize signal to noise ratio, then this shows the final result. Then maximal signal to noise ratio is proportional to square root to t, and it has a factor of this, and this is the overlap reduction function scale, and this is the scale of power spectral density, and these two factors are noise spectral density for each detectors. And if we have several detectors, then the effective total measurement time is increased by number of pairs for n detectors. So the effect for several detectors is increasing the total observational time. So the time is increased by n scale, so signal to noise will be proportional to the number of detectors approximately. Okay, then I can introduce working principle for pulsar timing arrays. Firstly, I introduce millisecond pulsar. Actually, each rotational period is smaller than 10 millisecond, and it has an extremely stable rotation. And this is a pulsar catalog. X-axis shows the log of period of pulsar, and each point is a pulsar. And y-axis is a relative change of period with the log. So in millisecond, the pulsars in this circle is approximately millisecond pulsar, and each relative each change of period is extremely small. It means that it has a for millisecond pulsar, it has a extremely stable rotation. Actually, firstly, neutron stars are the new baby neutron stars are birth of neutron stars started from this region. But if neutron star has a companion star, then it can absorb the angular momentum from companion star by absorbing matters. Then the rotation speed is increases by the matter. Then pulsars move to this region. Then in this, so millisecond pulsar usually has a companion star. Then rotating neutron star has a magnetic axis. So if a magnetic axis is a sweep, if we sweep our line of sight, then the signal, electromagnetic signal of a pulse has a peak when the magnetic axis is aligned to our line of sight. Then if we have a radio telescope, then this diagram shows the intensity of pulse over the time, and it has a very regular peaks, and each the period is very stably constant. But when electromagnetic wave pass through the space-time and pass through the gravitational wave, then electromagnetic wave is perturbed by gravitational wave. So its period will be changed slightly. So the fractional change of this period is the output of can be means of gravitational wave observation, and this is the output of this type of detector. Then this output has a gravitational wave signal contribution from gravitational wave and noise. And actually, noise is much larger than the gravitational wave signal, and there are main noise sources. Main noise sources are interstellar medium of the path of electromagnetic wave, and the pulsar itself has a irregular irregular rotation, so there can be a intrinsic pulsar noise, and radio telescope has a temperature, so it can have a detector noises. But all noises can usually is much larger than gravitational waves. So for this observation scenario, we cannot observe gravitational wave. Actually, noise is much larger than gravitational wave. These are exact form for gravitational wave signal. I will skip this detail. But if we use the two pulsars, then if we correlate output, then gravitational wave is amplified, and other terms will be canceled relatively to these signals. So if we measure increasing observational time, so we can amplify gravitational wave from the output for two pulsars. And the correlation of H1, H2 has an angle dependence, C alpha. Actually, alpha is the angle between two line of sight of two pulsars. And this is the curve for alpha dependence for this proportional coefficient. Then actually, there are some angles to become C alpha vanishes. So when the two pulsar has this angle, then we cannot observe a gravitational wave by this correlation method. But the angle is goes to 0, then we can have a most gain for gravitational wave, as seen by this figure. And this figure shows nanograv 15 years result. Actually, this violin shape is determined from Bayesian calculation, and Bayesian is determined by proportional to likelihood and prior, and inversely proportional to evidence. And blue line shows the Bayesian posterior of the overlap reduction. So actually, C alpha is the overlap reduction. So C alpha is equal to this overlap reduction. And by Bayesian calculation, this violin shows the posterior probability density. So the most probable position is shown by this horizontal solid line, and the horizontal solid line, which means that median and 68% credible values. And the nanograv result reports the Bayesian analysis for this overlap reduction is matched to the Hellingsdale's curve. Hellingsdale's curve is a theoretical prediction of overlap reduction. And this is the target source for pulsar timing array, and it has a frequency band from 10 nanohertz to the 10 to the microhertz. And actually, the nanohertz determined from the total observation time. It is about 10 years, and the microhertz determined by cadence for observation. So it is about 1 week. So each pulsar timing array over the world has a observation cadence about 1 week or 2 weeks. And all over the pulsar timing over the world collaborating into international pulsar timing array. So if they collect all the pulsars, then if we collect all the data, then we can observe 100 millisecond pulsars. So actually, the these are all over the these are telescopes used by each pulsar timing array collaboration. And this is the Square Kilometre Array Observatory. It actually is the future of radio telescope, and it will started from 2028. If this SKAO started, then
So question in your previous the picture.
Okay. Yes.
So according to your explanation, to get rid of the noise, seems
Yes.
that we do need at least more than two or more detectors, right?
Yes, right. 2 or more.
Does it mean that the Chinese radio telescope, which is very large, fast, so by itself, it cannot detect any pulsar timing array? They cannot get any signal, or?
FAST can observe the several pulsars.
Yeah,
So
pulsar is okay, but I mean, question is whether we can see stochastic gravitational wave background, right?
yes, I can observe stochastic gravitational background, and
But you said the noise is much bigger than the signal, and to get rid of the noise, seems that you do need you explained that we need more than two detectors or something, no?
okay. Actually, the first, actually for one telescope, we can observe the several pulsar. It means that we can have actually the pulsar timing array is the galactic scale detector. It means pulsars are in our galaxy, and this line shows the detector arm. So the pulsar and line between pulsars and telescope is itself the detector for gravitational wave. So it means if we only have one radio telescope, but it can measure many pulsar in our galaxy, then we have many arms for to detect gravitational wave background. So we can have
I
a
see.
output. Yeah.
I see. I understood. Thank you.
Okay. Okay. If the SKAO is start from 2028, we expect that 1,000 millisecond pulsar can be observed simultaneously. It means that as I explained, if we have many output or many detectors, then the effective total measurement time is increased by the total pair of all output. So the signal to noise ratio is proportional to total number of detectors. It means that the international PTA can amplify signal to noise ratio by factor of 100, and SKAO can amplify the signal to noise by thousand factor. And SKAO has two sites. First one is SK-low is in Australia and SK-mid is in South Africa. But I expect the SK-low will measure will observe pulsar, millisecond pulsars. Okay, let's move to the next part. Time is very limited, so I will show quickly. Let's consider the supermassive black hole binary as a source for gravitational wave background in nanohertz. In galaxy merger, there are supermassive black holes inside the core, and it forms supermassive black hole binary. But if the star, there are star with the star and gas pressure can hardening the supermassive black hole binary, then binary is in subparsec scale, then it starts to merge and it can generate very strong gravitational wave, and finally it forms another supermassive black hole. But the gas pressure or star hardening is not enough, then it can be stored. But by another supermassive black hole is interacted, then this three-body process, it can have a binary in subparsec. But it is failed, then it can be stored as a supermassive black hole binary. So in this scenario, we cannot get enough gravitational wave power, but only this channel we can get the strong gravitational wave background from this scenario. So actually, in actual numerical simulation, many simulation failed to the supermassive binary is to become supermassive binary, let supermassive black hole binary to in subparsec scale. So actually, it is the very famous problem, so-called subparsec problem. So the gravitational wave background, if this channel, this scenario is possible, then the supermassive binary black hole cannot generate gravitational background. And this plot shows the Bayesian analysis for spectrum. Y-axis, x-axis is the gravitational wave frequency, and y-axis is the characteristic strain of gravitational wave. So the dotted line shows the theoretical expectation for circular supermassive gravitational wave background from circular supermassive black hole binary. So it has a power law. Power is -2/3. But the supermassive binary black hole supermassive black hole binary can have eccentricity or spin. Then from each effect, we have a purple line. Purple line is a theoretical expectation by including eccentricity and spin. And blue line is a more complex model, and it includes the gas and stellar-driven process. And it can have a turnover at low frequency. But in nanograv data, this probability density violin shape plot shows the Bayesian posterior result by parameter estimation, and each model has fitted by this Bayesian result. So actually in low frequency it has a peak, but in higher frequency the shape is very broad, so we cannot identify the peak of the posterior. So our data is not enough to distinguish these three models. So we cannot determine how the gas and stellar driven process are. And actually, the another model can be solved in this situation. Actually, the by only considering this posterior result, we cannot conclusively say we observe the gravitational wave background from supermassive black hole. So there are another possible scenario can be proposed to explain this data. And I want to introduce this very interesting project, PTArcade. PTArcade is the source program that is estimate the parameter of my to estimate parameter of my own GMB model. Then we can utilize PTArcade project, and it automatically imports the real PTA data from Nanograv and IPTA collaboration, and it can analyze very easily. And this is the homepage for PTArcade. And if we define our model, and we have a two parameter A star and F star, then just put in the code like that. Then this is the run code, run command for PTArcade. Then we can easily generate this type of parameter estimation picture, and this is the posterior of for A star, and this plot shows the posterior for F star, and this is the contour plot for parameter estimation. And credible for the blue line shows the credible region for two parameter. So using this using PTArcade, we can easily fit our model with observed PTA data, and our model can be constrained by PTA data very easily. Okay, I don't have much time, so I will skip this section, and I will summarize. Gravitational wave background is superposition of gravitational wave from unresolved sources, and gravitational wave has two origins, cosmological and astrophysical. And PTA is a galactic scale gravitational wave detector using millisecond pulsars, and PTA target gravitational wave in nanohertz band and required a period of observation about 10 years. And now the most plausible source of gravitational wave background in nanohertz are supermassive binary, but it is not conclusive. And SKAO is the future of PTA. Okay, that's all. Thank you very much. Is there any question?
Yeah, any question, please?
Yes, I have a question. Can you go more previous slide?
Okay.
The stochastic, the noise, the slide about noise.
Noise.
There is a picture. Yeah, this one.
This one? Yeah, okay.
So it seems that you assume that the noise are local and random. So
yes.
So what if some systematic noise is given? So that is generated by something else that, for example, propagating light waves, propagating light electromagnetic waves.
Actually, I don't know where systematic noise. I don't understand the question.
So it seems to me that you are assuming that the noise is random and local. So there is no correlation between detectors.
Okay. Yeah. actually noise are come from all the thing from the source of electromagnetic wave and from the receiver of electromagnetic wave and space the gravitational wave passes. There are interstellar media, and the interstellar medium from this region and this region, there is no correlation. So gravitational wave is also this term will be uncorrelated, and this term is the correlation between gravitational wave and noise. But the gravitational wave is generated from many unresolvable sources, so there is no correlation with interstellar medium, and so this term will be vanishes. Is it? I don't know whether it is a correct answer.
I don't know. Okay, so my question was, what if the noise was generated by something else that sweeps all the detectors on Earth? So
Earth.
yeah, so in that case, the noise can be systematic.
Yeah. Okay. Yeah. Right. Yes. But usually the noise from Earth is classified usually classified as the Newtonian noise, and it comes from the seismic noise and or infrasound from atmosphere. But the typical most strong frequency band for this Newtonian noise is 0.1 to 10 hertz band. So in our nanohertz band, the noise from Earth can be negligible. Actually, the most important noise for in nanohertz band is comes from the motion of Earth and Sun and other planet. Actually, our center of mass of a solar system is not fixed at the Sun, because Sun will be moved to the center of mass, because the Jupiter can affect the Sun, so their center of mass is has an opposite from the center of Sun, and actually it is called the timing noise. So we have to know the exact position of Earth and Sun and Jupiter, and from the our mass center of solar system. And the Earth has a motion, so it has a relativistic effect, special relativistic or general relativistic effect of time shift. So it can be a noise, kind of a noise budget.
Okay, yeah, thank you.
So, but there are actually the personal memory observation is very challengeable because there are many noise budget we have to solve.
Okay, thank you.
Any other questions? All questions? Okay, if there is no question, then let's thank Dr. Chan Park.
Thank you very much.
Thank you very much.
박찬 박사님,
예.
죄송한데 그 박사님 이메일 릴리아나 박사님한테 좀 드려도 되죠? 아, 이게 인터넷 커넥션 때문에 제대로 못 들었대요. 그래가지고
아, 예, 예, 예. 예,
저
됩니다. 예,
연락이 와.
예. 저도
예,
뭐가
알겠습니다. 예.
소리 좀 안 좋긴 한데, 예, 예.
예, 재밌게 잘 들었습니다, 박찬
여기 뭐
박사님.
자유롭게 질문하실
예.
분들 좀
예, 질문하셔도 됩니다. 한국말로 하셔도 됩니다, 이제.
오피셜링 끝난 거죠?
예, 예.
예.
아, 오늘 정말 못 가서 죄송합니다.
아, 아니에요. 그 IBS에서 조금 제동이 있었나 봐요. 예.
예, 아, 좀 그렇게 됐습니다. 연기 문제가
예,
있어가지고.
예, 예. 그 혹시 이제 이게 지금 이제 그 대부분의 포멀리즘이 다 이제 아인슈타인 티어리에서 이제 만들어진 포멀리즘인데
예,
그 몇 페이지인지 제가 까먹었어요. 그러니까 그 그래비테이션 웨이브 스펙트럼 있는 쪽에 혹시 오메가 뭐 이렇게 해가지고
예, 예, 여기, 예,
예, 이런 쪽에, 예, 이런 쪽에서 만약에, 아인슈타인 티어리가 아니고, 만약에 이제 우리가, 만약에 그 가우스본의, 이제 박사님도 잘 아시니까, 가우스본의 딜라톤 커플링이 있는 티어리가 된다면, 이런 데에서 좀 변화가 있게 되죠. 혹시 그 참고할 수 있는, 혹시 답변을 아시거나,
예,
참고할 수 있는 레퍼런스 같은 거를 이렇게 좀 알 수 있을까요? 아마, 뭐, 릴리아나도 아마 비슷한 질문일 가능성이 좀 많아요.
예.
다른 띠어리에서 막 이걸 하고 있어가지고
제가 알기로는 띠오리를
예,
바꾸면 이제 폴라라이제이션 개수가 늘어나서
예, 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 예,
그런 효과가 이제 가장 큰 걸로 알고 있고요. 그러면은 이제
예, 예,
이 폴라라이제이션 요 그 어썸션이요.
예,
요게
예, 예,
남자
예,
LBD가 아니라
음,
그냥
음, 음.
그냥 G 이게 프로젝션 이런 트레이스 리스트 파트도 사라지고 이게 뭐라
어허,
해야 되지? 이게 그냥 매트릭으로 쓰여질 것 같아요. 이게 그러니까 뭐 G 뭐 이런 데서 막 많은 시메트릭은 해야 되니까
그,
뭐 만약에 모든 폴라레이션을 프리퍼 안 한다면 6개 폴라레이션이 다 있고요.
예, 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 예,
안
예,
한다면 막 이렇게 바뀌어 일단 이런 것들이 바뀔 것 같고요.
예, 예.
그리고
혹시 그런 그 레퍼런스, 그러니까 좀 참고할 만한 논문 같은 거를 조금 이렇게
아,
알고 계신지
제가
아니면은 잘 몰라서 물어보는 거예요. 우리 어떻게 해야 될지.
예전에 좀 찾아본 적이 있는데 그
음,
폴라레이션
음.
6개 그게 예전에 근데 이제 그게 일본 사람들이 쓴 논문이 좀 좋아서
예,
그거를 봤던 적이 있는데요. 그거는
예,
스토캐스틱
예.
그러니까 중력파 백그라운드에 대해서는 얘기 안 하고 있고 일반 중력파 그냥
음.
바이너리 머저에서 온 그런 이야기를 주로 하고 있는 것 같아서
예, 예,
중력파 배경 쪽에는 좀 도움이 안 될 수도 있고요.
예,
아,
예.
잘 모르겠습니다. 사실 제가 좀 서치를 많이 해본 게 아니라서.
자, 사진은 막 찾아보려는데 잘 못 찾겠더라고요. 그래가지고, 그 나중에 이제, 뭐, 제가 이제 개인적인 얘기는 하긴 그렇고, 나중에 제가 따로 이메일로 또 한번 좀 물어보던지 할게요, 그러면. 예,
그 보통
물어보거나, 예,
제목이 그
예,
뭐지? 뭐라고 부르던데 그 중력 이론 중에서도
예, 예.
그
조금 오래된 거, 그러니까 뭐, 브란스 티켓 티어리 이런 거요?
예, 브란스티케를 포함하는 그걸 뭐라고 부르죠? 그
스칼라 텐서 티어리?
칼라텐서 시오리 맞아. 그런 식의 제목으로
예,
많이
예.
쓰여진 것 같아요. 예.
그러니까
음,
지금 이제 그 리치 스칼라의 리니어한 거에 이제 커플이 되느냐? 이제
예.
우리는 이제 가우스 본네 이제 뭐 어떻게 보면 이제 제곱한 꼴이잖아요.
예.
이제 거기에 이제 커플이 되느냐? 그것 때문에 효과가 어느 정도 있을 수 있나? 막 이제 사실은 좀 의구심도 좀 들고 예, 예. 예, 이건 뭐
예, 제가
만났
한국말,
예, 예. 말씀해
죄송합니다. 네, 말씀하십시오.
아니요, 말씀해 주십시오. 예,
예,
제가
제가 한국말로 아까 질문을 다시 좀 드려볼게요.
예, 예, 예.
그 이제 중력파의 어떤 점이 이제 그 효과가 매우 작음에도 불구하고 다른
네.
노이즈들을 다 이기고 그게
예,
이제
예.
우리가 디텍트 할 수 있게 돼 있는지 콕 집어서 좀 직관적으로 설명해 주실 수가 있나요?
일단 이 그림이긴 한데요.
네,
우리가 이제 두 디텍터한테 가해지는 중력파는 동일한데,
네,
뭐 거기에 있는 노이즈는 랜덤이기 때문에 서로 관련이 없을 가능성이 높고요. 만약에 디텍터가 충분히 멀다면
예,
예, 그런 경우에 이제 우리의 아웃풋이라는 게 이 H와 N의 합이거든요. S라는 게 H 더하기
예,
N. 그거에
예,
이제
근데 이제 요 경우는요, 그 이제 밑에 그 파란, 위에 파란 걸로 표시된 게 같으면은 다 디텍터가 될 수 있는 거잖아요.
예,
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 예. 그러니까 이제 뭐 전자기파 같은 게 지나가면서 지구 디텍터를 다 훑고 지나가면은
예.
그 똑같이 이제 작용될 수가 있잖아요. 코릴레이션이 있을 수가 있고.
예, 그럴 수 있죠. 그리고 한 가지 더 제가 또 그 부분이 또 있고요.
예,
그다음 이 헬링스 앤 다운스 커브 이 부분이 또 뭐가 있냐면 이게 앵글
예,
디펜던시잖아요.
예,
이게 중력파에서만 나올 수 있는 앵글 디펜던시거든요. 그래서
예,
이게 다른 노이즈나
예,
전자기파는 이런 앵글 디펜던시를 못 만들어요. 그래서 아마 이
예, 예.
디펜던시도 중요한 기준이 됩니다. 예.
예, 그게 예, 중요하겠네요. 예,
예.
예, 감사합니다. 한국말
예.
하는 거 좋네.
예.
예.